Welcome back. Today we will be continuing our studies in Chapter 8, looking at hypothesis testing, and we're going to specifically be looking at Section 8.3, which is talking about hypothesis testing involving a mean. So I have a warm-up here for you to do that involves the hypothesis testing for proportions. So I'd like to give you some time to pause this and then work through it and check your answers on the next slide here. So go ahead and try this. Okay, so what you should have done is to identify your claim. So the claim on this one is that more than 20% of users develop nausea. And because our claim statement has a percentage in it, it's going to be a proportion type hypothesis test, which at this point is the only type we know how to do. But after today's lecture, you will know other types as well. We'll identify our values. So our N was 206, X was 50, our significance level was 0.01. The P, which always comes from the claim, is 0.20 because we see that here. And then P hat is X over N. So divide that out and you get this value for the P hat. You do need to verify your requirements. So the first one, we just make that assumption. And even the binomial part, they either did or did not develop nausea. So the main thing you're looking for there is the two categories. The third one, though, you do need to show me this. So if this were on a test and I was asking to see work, I would want to see these requirements being demonstrated to me. So check that. Make sure that these, when you multiply N times P, is going to be greater than or equal to 5, which they both are. So next we're ready to set up our null and our alternative hypothesis. So we know that the null hypothesis always gets the equals. P is always the parameter that's used when it's a proportion type. And the value that we're going to use here in the null and alternative hypothesis comes from the claim. So that's this 20%. And since it says more than, we're going to use a greater than symbol here. So what we see is that this is a right tail test because of the greater than symbol. We also can tell that this is our claim statement here simply because it matches. This is the symbolic representation of this claim statement. If we were to look at our flow chart, the flow chart asks, is the claim in the null hypothesis? And in this case, the claim is not in the null hypothesis, and so it's in the alternative, and that's what we're trying to decide here. So we see that our claim is in the alternative hypothesis here. We'll do our test statistic, plug in our P hat and our P. Be sure you've got parentheses around that, and put in the PQ over N. Remember that Q is 1 minus P. And then we're going to find the p-value. So we said this was a one-tailed test, so I'm going to put 1.53 on the right since it's a right tail. Shade that in, and I'm going to do the normal CDF to find the area of this curve here. That's going to tell me the probability of getting a test statistic at least as extreme as 1.53 or more so. So when I do that, I get the 0.0630, and since it's a one-tailed test, that's going to give me the p-value for that. And as far as my conclusions go, if I compare this to the alpha, which is what you always want to do, compare the p-value and the alpha, my p-value is larger than the alpha, so my conclusion is going to be that I failed to reject the null hypothesis. Okay, so I'm ready to write my non-technical conclusion, and my statistical conclusion was that I failed to reject the null hypothesis. So basically, I'm not able to throw this out in support of my claim. So anytime that our claim statement is in the alternative hypothesis, you need to speak about whether you're going to be able to support or not support the claim. So here, since we're not able to throw this out in favor of it, then we're going to have to say there is not sufficient evidence or there's not sample data to support the claim. So we're not able to support the claim with that. So if you were to be looking at your flow chart, the claim is in the alternative hypothesis, so it's not in the null hypothesis. And then when you go down and you see that you failed to reject, that's going to take you to this statement here. Okay, like I said, today we're going to be looking at section 8.3, and that's going to involve testing a claim about a mean. So there's two sections to this. The first one is the one that we're primarily going to focus on, and that is when our population standard deviation is not known. Okay, and that's the case most of the time. We are going to briefly talk about if this population standard deviation is known, but that's actually a fairly rare event for that to occur. So we're going to focus on the not known case. Okay, so our objective, we're going to use the hypothesis testing to test a claim about the population mean mu. So in this case, instead of estimating a population proportion, we're going to be estimating a population mean or average. Okay, so when we look at testing a claim about a mean, it's just like writing a confidence interval about a mean. We have to go through this process where we decide whether to use a Z or T. In the case of confidence intervals, it was a Z or T critical value, but in the case of hypothesis testing, it's a Z or T test statistic. So we're going to ask the same question, is the population normally distributed or is n greater than 30? If neither of these are true, then we have to stop. We're not able to proceed at this point. If one or the other or both is true, then we can go on to the next question, which says, is the population standard deviation known? Okay, normally if it's known, it's going to come out and say the population standard deviation is such and such. If it's saying that just the standard deviation and it's referencing the sample, then that's an S. And anytime we have an S given for our standard deviation, then we're going to use a t test statistic. Anytime we have the sigma that's known to us, then we're going to use a z test statistic. Okay, so some symbols just to kind of reiterate here. N for your sample size, X bar is your sample mean, S is your sample standard deviation. So you can have sigma, which is your population standard deviation. I think a lot of people get confused and think because it has the word standard deviation in it that all standard deviations are the same. It depends totally on where it's coming from. Sigma comes from the entire population. S is coming from a given sample. So you really have to use your context clues, just like you learned about when you were reading in elementary school or something. Look at the context of the problem and see where those originate. Do they originate with the entire population, or do they originate with the given sample that you're studying? And then mu of X bar is your population mean. Okay, for our requirement check, it's the same as the requirement check for the mean when we were talking about confidence intervals. That is, the first one has to be a simple random sample, and then the second is that it either or both has to be true, that it's normally distributed, or n is greater than 30. Okay, our test statistic that we're going to use when we test a claim about a mean when sigma is unknown is going to be X bar minus the mean divided by the standard deviation over the square root of n. I would suggest two sets of parentheses, one here and one here when you're entering it in your calculator. Okay, so one thing, if the original population is not normally distributed, we can use this condition that n is greater than 30 to justify the use of the normal distribution. But even for samples of size 15 to 30, as long as they're not far from normal, we're kind of able to go ahead. So this is somewhat of a loose interpretation of this. So when you're looking at maybe a normal quantile plot or a histogram, if they're not perfectly normally shaped or perfectly a straight line, usually it is still enough to go ahead with this process. Okay, so we are going to be using this student t-distribution again, and again, to just recap that, it is different for different sample sizes because we have to work with the degrees of freedom. So the degree of freedom is one less than your sample size. It's a bell-shaped curve, much like the normal distribution has a mean of 0 and a standard deviation. The standard deviation is going to vary with the sample size and is going to be greater than 1. And as the sample gets larger, the student t-distribution actually gets closer to the standard normal distribution. Okay, so here's an example that I want us to go through. The first thing I want you to do is to pause the video and get this data set entered, because anytime you have a data set in this class, the first thing to do is to get it in your calculator so that we can work with it. So go ahead and enter that data and then read this and underline your claim. Okay, so this is a data set of 12 values that you need to have entered in your calculator. And I ask you to go ahead and identify the claim. If you read through this, it says a common recommendation is that adults should sleep between 7 hours and 9 hours each night. Use the p-value method with a 0.05 significance level to test the claim that the mean amount of sleep for adults is less than 7 hours. So here is our claim statement, and you can see that the claim is talking about a mean. So last class we talked about claims that referred to percentages. Claims that refer to percentages are going to be testing a proportion. Here, claims that refer to a mean, we're going to do with a different technique here. So if I read through this, I do not see that there is a population standard deviation given to me. So that means that I'm going to need to get some of this information from the data set. So I'm going to switch over to my calculator. Okay, so we have the data set entered in our calculator. So we want to do the stat calculate one variable statistics for L1. Okay, so here is the X bar that we're going to need to be able to use, and here is the S sub X. This is our standard deviation of the sample. Do not use this value, okay? Use the S sub X for the sample standard deviation. So while I have the calculator up, I want to go ahead and mention that it did not tell us that it was normally distributed. So what we're going to do is we need to actually look at a normal quantile plot. If I turn that on and then make sure you've highlighted the sixth graph, and I need to switch this to L1, and then I'm going to do zoom number 9 for zoom stats. So what I see here is it's definitely not a perfect straight line, but it is fairly linear in nature, and it's enough for us to be able to go ahead with our process here. So when you're not told whether it's normally distributed and your sample size is not more than 30, but you have your data set, then your calculator can help you figure that out. We could have also looked at the histogram, and the histogram you'd want to see a normal symmetrical bell-shaped curve with that. Okay, so if we go ahead with this, we said that you enter your data, and from one variable stats, you're going to see the X bar is this number and S sub X is given here. So that's what we're going to use to complete our problem. So for the requirements, we mentioned that while we had it on the calculator, we wanted to go ahead and verify that it was normally distributed. So if we look at our histogram and normal quantile plot, we can see that they both indicate that it's approximately normally distributed. Certainly not a perfect normal distribution, but it's close enough for us to go ahead with it. Okay, so we want to set up our null and our alternative hypothesis. When we look at our claim is about the mean, so we're going to use mu instead of the p. So for proportions, we put a p here. For mean, we're going to put the mu. The null hypothesis is still the equals one, and we still go to the claim to get the value. So our value is 7 hours. And here we're talking about less than 7 hours, so that's going to be our alternative hypothesis. That is also our original claim because this is the symbolic representation of what this claim is stating for us here. Okay, for our test statistic, because sigma was unknown, we did not know that in this problem, that tells us that we need to use a t-test statistic. Okay, so for our t-test statistic, this is the formula that we're going to use. Remember I said put parentheses here and put parentheses here when entering it in the calculator. So our X bar we got from our one variable stats. Our mu was from the claim statement. Our S was from the calculator, and then our N was our sample size. We had 12 data values, so we'll put the square root of 12 here. When you do this calculation, you get this value, and that is our test statistic. Okay, so what I want to do is I want to find my p-value. This is going to be a little bit different. We're still going to put it on the curve, except this time it is a t-distribution instead of a normal distribution, but it still looks the same. Okay, we're going to draw in here and put our test statistic, which was negative 0.290. It's a left-held test, so we're going to come from negative infinity to this value here. The difference is because it is a t-test statistic, we have to use the t-CDF. So if it's a z-test statistic, we use a normal CDF. But if it is a t-test statistic, we use a t-CDF. Okay, so it's set up the same way. It's still going to be the left, the right, except we're going to, because the t distribution is a family, we have to include the degree of freedom. So it's still left bound, right bound, and then your degree of freedom with that. So the place it's going to be located at is the distribution menu, the same place you go to for your normal CDF and your inverse norm. So just down a little bit further, you should see t-CDF. As far from my experience, everybody has this. Not everybody has inverse T, but as far as I know, everybody has a t-CDF that uses a TI 83 or 84 or the plus versions of either of those. So enter your lower and upper bound, your degree of freedom, and when you do that, you come up with this value, and so that's going to be your p-value that you're given here. So I don't need to double it because it's a one-tailed test. It was a left tail. And so from that we can get our p-value. All right, so finally for our statistical conclusion, remember we always compare the p-value and the alpha. So my p-value we found to be 0.3887 and the alpha was stated to be 0.05 in the problem. So my p-value is larger than my alpha, and so my conclusion is that we failed to reject the null hypothesis. So we still need to make that comparison there. And then for my non-technical conclusion, I'm actually going to go back here to my null hypothesis. Okay, so our statistical conclusion was that we fail to reject the null hypothesis. Okay, so if we're failing to reject this, then we've got to kind of hold on to it. We're not able to throw that out in favor of or in support of this alternative hypothesis. So what we're going to say is there is not sufficient evidence to support the claim that the mean amount of sleep for adults is less than 7 hours. Okay, so we conclude there's not sufficient evidence to support the claim that the mean amount of sleep is less than 7 hours. Okay, if we want to do this on the calculator, you can go to Stat, Test, and T-Test. And then because this one had data provided, then you choose Data. If you already had your summary statistics provided, then you choose Stats. Enter the mu, that's going to come from your null hypothesis. Enter your X bar and your S if you need to. Now, if you're choosing Data, you're probably not going to have to enter the X bar and the S because that is going to all be taken from the data set you enter. Choose the tail type that you're going to work with and calculate. So if we go to Stat, go over to Test, and we're going to choose number 2, T-Test. This one we had our data entered, so I'm going to choose Data. And our null hypothesis was 7, and we had the less than. My data was in L1, and our alternative hypothesis was the less than. So if we go down and calculate, then here's the test statistic, and here's our p-value that we found. So these should match up. They may be rounded slightly different, but they should basically match up with that. Okay, so at this point we have 2 hypothesis tests that we can do on our calculator. For the proportion, we choose one proportion z-test, and for the mean with sigma unknown, we choose a t-test. Okay, here's one that I want us to go through. If you feel comfortable and want to try it yourself, then certainly do that. If you don't, then just keep going with the video and listen to what we've got, what we're going to do. So here we have a sample of 106 body temperatures was gathered, which had a mean of 98.2 degrees Fahrenheit and a standard deviation of 0.62 degrees Fahrenheit. Use a 0.05 significance level to test the common belief that the population mean is 98.6 degrees Fahrenheit. So there's been some controversy of late as to whether 98.6 is actually the mean body temperature. Some data says that it's maybe a little bit lower than that, and so this is kind of testing that claim there. So on this particular one, we're wanting to test the common belief that a population mean is 98.6. So this is my claim statement here. Okay, from this, I need to identify my values. So I have a sample size of 106. I have a mean of 98.20. So that's the mean of my sample. So that's X bar. And the standard deviation, again, these two values are originating from the 106 data values. So because of that, these are sample values. So this is an S and not a sigma. This is going to be my alpha. Okay, so I could list my data values, or not my data values, but my summary statistics. 106 for my N. X bar is 98.20. S is 0.62. Alpha is 0.05. And then this is actually going to be my mu. Okay, so this is coming from my claim statement, so that's going to be my mu. I could go ahead and check my requirements because we need to know that it's a simple random sample, and we also need to know that it's normally distributed or n's greater than 30. Obviously, we have a fairly large sample size, so we're good with that part. If I go and set up my null and my alternative hypothesis, the claim is about the mean, so I'm going to use mu. The null always is the equals, and then the value that's in the claim is the 98.6. Okay, and there's no indication of a direction in the claim, so we're going to go with does not equal. Okay, we're ready to look at our test statistic for this problem. So our test statistic on this one, because sigma was still unknown, we're going to use a t-test statistic, which is X bar minus the mean divided by S over the square root of N. So my X bar in this case was 98.2. My mu was 98.6. My S is 0.62. And my N is the square root of 106. Okay, so put parentheses here, and then put that in your calculator, and we get a test statistic of negative 6.64. Okay, our null hypothesis, or our alternative hypothesis, excuse me, was a does not equal. So because of that, if we look back here, this tells me that it is a two-tailed test, and that's going to be important. So when I look at finding my p-value, I need to keep that in mind. Okay, so this is a t-distribution. I have a test statistic of negative 6.64. And I need to find this. Be very careful because the kind of the habit that we have is to do a normal CDF, but because this is a t-test statistic, we're going to need to do a t-CDF from negative infinity to negative 6.64, and our degrees of freedom on this one is actually 105 because our sample size was 106. Our degree of freedom is one less than that, so that's going to be 105. And so that on your calculator is going to be 7.09745. Actually, sorry, not a 5. I can't read my writing. E to the negative. Okay, E negative 10. So basically what that is that's 7.0974 times 10 to the negative 10th. Or if I wanted to move that decimal, I need to move it 10 places to the left. Okay, and so this is what I get. And that's basically 0 for all practical purposes. One thing, this is a two-tailed test as we talked about. So we actually also have that same area over here. So you do want to make sure that you go and double this. But when I double that, I'm still going to basically get a value that is 0 plus for my p-value. I do want to see, even if it's a case like this, I at least want to see that you let me know you know to multiply that by 0. By 2. Obviously, 0 times 2 is still 0. but show me that you know that this would have been necessary to multiply it by 2 in order for you to get credit on the problem. Okay, so we want to do our statistical conclusion. So we're going to compare our p-value with our alpha. So 0, and then we said our alpha on this problem was 0.05. So the p-value is smaller than the alpha, so that tells me I'm going to reject the null hypothesis. So my statistical conclusion would be to reject the null hypothesis. I'm going to go back now to write my non-technical conclusion. If I look at this part, this is where my claim statement is this time, because we're testing the common belief that the population mean is 98.6. So that would be this statement here. So this is my claim statement, and I just said that I'm going to reject the null hypothesis. So by rejecting the null hypothesis, I'm actually rejecting the claim. So I would say there is sufficient evidence to warrant rejection of the claim. Remember, when the claim is in the null hypothesis, your statement is going to talk about whether or not you reject the claim. When your claim is in the alternative hypothesis, you're going to talk about whether or not you support the claim. Okay, so if you want to see that written out, there is sufficient evidence to warrant rejection of the claim that the population mean temperature is 98.6 degrees. Okay, if we were putting this in the calculator, just to kind of show you, you're going to get a p-value that looks like this. So don't just disregard this. A lot of people will tell me the p-value is 1.40. Make sure you notice this and move your decimal an appropriate amount of places. It is a two-tailed test, so your calculator has already doubled it here. You don't need to double this value. It has already doubled for you. Okay, so this one, again, if you feel comfortable and want to try it, go for it. Otherwise, just listen to this, to what we're going through with this example. A researcher wishes to test the claim that the average cost of tuition and fees at a four-year public college is greater than $5,700. I do think this is an older problem that probably needs its numbers updated a little bit. She selects a random sample of 36 four-year public colleges and finds the mean to be 5,950 and the population standard deviation is 659. Is there evidence to support the claim at a 0.05 significance level? Okay, so if we look at this, here's our claim that the average cost of tuition and fees at a four-year public college is greater than 5,700. So we know average is kind of the layman word for mean. So mean is the statistician word that we're going to use. So the mean cost of tuition and fees is greater than 5,700. So as far as the type we're doing here, this is a mean type because we're testing a claim about the mean. So when I go to identify my values, I see that n is going to be 36. Okay, the mean of my sample, which is my x bar, is 5,950. And then if we look here, we're actually told the population standard deviation is 659. So my population standard deviation is sigma. This is where knowing your symbols is very important. Okay, we've got an alpha that is 0.05, and the only other value we've got is the 5,700 that comes from our claim. So the one that's coming from the claim is going to be my mu. All right, so we're ready to look at the requirement check. We're going to assume it was done as a simple random sample. And then second, we want to make sure it's either normally distributed or n is greater than 30. Our sample size is 36, so we're good to go with that. Okay, so we want to set up our null and our alternative hypothesis next. We said that when we're testing a claim about the mean, this is going to be mu. So that does not change whether the population standard deviation is known or not. We're still going to set up this the same way here. Okay, the value that we're testing in the claim is the 5,700. And this one, we're saying that the average cost is greater than 5,700, so we're going to do the greater than symbol there. So this is actually going to be my claim statement here. Okay, so for the test statistic, because sigma is known, we're going to use a z-test statistic. So my z-test statistic is going to be x bar minus the mean divided by sigma over the square root of n. So that's what I'm going to substitute into. So when I substitute in here, x bar we said was 5,950. Mu is 5,700. Sigma is 659, and n is 36. So when I put that all in my calculator, I get a test statistic of 2.276. Okay, moving on, our next step is to find our p-value. So because this is a z that we're working with, our z-test statistic, we're going to use a normal distribution. So this is back to a normal distribution. We said that our z-test statistic is 2.276, and this is a greater than, so it's a right-tailed test. So we're going to be solving for this part. And so we're going to do a normal CDF because this is a z-test statistic. If it had been a t-test statistic, we would do a t-CDF. So we'll do 2.276 to infinity, and that's going to give us 0.0114 as our p-value. It's a one-tailed test, so we don't need to double this. Okay, so for our statistical conclusion, we want to compare our p-value with our alpha. So the p-value is 0.0114, and the alpha is, for this one, 0.05. So the p-value is smaller than the alpha, and so if the p is low, the null must go. So we're going to reject the null hypothesis. Okay, so at this point, I'm going to look back at my alternative here, my null and my alternative, and I see that the claim is in the alternative. So my conclusion was that I'm going to reject the null hypothesis. So I'm going to reject that in favor or in support of my claim. And that's what my statement's going to read. It's going to say there is sufficient sample evidence to support the claim that the average cost of tuition and fees at a four-year public college is greater than $5,700. Okay, so if we wanted to do this one on the calculator, what we would do is we would go to our test menu, and this time we would choose z-test because that's what we would use if we have a z-test statistic and we're trying to find test a mean. So here we had, instead of data, we had stats. So that's the one you're going to choose here, and it'll give you the opportunity to enter your null hypothesis value, your population standard deviation, your sample mean, your sample size, and then you can choose the tail. So this one had a greater than tail, and then calculate. And so here's the test statistic that we had found. And here is the p-value. And again, they may be slightly off just due to rounding, because every time we round within a problem, we're going to compound our error slightly. Okay, just to reiterate, if your test statistic is a z-test statistic, then you'll do a normal CDF, and if the test statistic is a t-test statistic, you're going to do a t-CDF. So if you're identifying your test statistic incorrectly, it's going to mess the whole problem up. So really be careful about identifying that correctly. Okay, this is our last example for today. So if you will try this one, I would like for everybody to try this one on their own and just make sure they can come up with the work and the conclusion that you should have for this. Okay, so on this one, a medical investigation claims that the average number of infections per week at a hospital in southwestern Pennsylvania is 16.3. A random sample of 10 weeks had a mean number of 17.7 infections, and the sample standard deviation is 1.8. Is there enough evidence to reject the investigator's claim at a significance level of 0.05? Assume the population is normally distributed. So we've got a lot going on here. Here's our claim. The claim is that the average number of infections per week at a hospital in southwestern Pennsylvania is 16.3. So average is indicating mean, and so this is going to be a mean type hypothesis test. Here we have 10 weeks, so that's going to be our sample size. And the 10 weeks, when they looked at the data from the 10 weeks, it had a mean number. So this is my X bar. That's the mean of the sample. So the sample mean is X bar. The sample standard deviation is 1.8. So that's going to be my S. Sample standard deviation is an S. We have our alpha. We know that it's normally distributed. So all that's important. If we identify our values, N is 10, X bar is 17.7, alpha is 0.05, S is 1.8, and the one other one that we hadn't identified here is the 16.3. Since that's coming from the claim, that's going to be our population mean, or mu. Okay, for our requirement check, we've got simple random sample, and then the other is that it's either normally distributed or N greater than 30. We are told that it's normally distributed, so we're good with that part of it. So we're pretty much ready to get started here. Our null hypothesis for this one, again, these are testing the mean, and the value in our claim is 16.3. Our claim statement is that the average or mean number of infections per week at a hospital is 16.3. So it doesn't indicate a direction. So this is going to be a does not equals problem. This is actually our claim statement, because if we translate it into symbols, what the claim is saying, this is the one that would do that. Okay, so our test statistic, if we look back at what we were given here, there is no mention of a sigma. There's no population standard deviation that's known. So what that tells me is that I'm going to have to use a t-test statistic since sigma is unknown. So I'm going to have x bar minus mu divided by s over the square root of n. So my x bar on this one was 17.7. My population mean that the claim that I'm testing is 16.3. The S is 1.8, and the N is on this one 10. Okay, be sure you have parentheses so that we don't get an order of operations error. And we get 2.4595. Okay, so we're ready to find our p-value, and I'm going to put that on here. It's a two-tailed test, so I have this side and I also have over here. And it's a t-test, so that tells me I'm going to do a t-CDF. My sample size was 9, so my degree of freedom is 1 less than that, or 8. So if you put that in the calculator, we get 0.0181. And we said it's a two-tailed test. We know that because it's a does not equal. So I'll multiply by 2. So I get 0.0362. And that is my p-value. Okay, finally, we want to compare the p-value and the alpha. So the p-value is 0.0362. The alpha is 0.05. So my p-value is smaller than my alpha. So if the p-value is low, the null must go. So we're going to reject our null hypothesis. Okay, so here we're going to have to reject this null hypothesis. So basically by rejecting the null hypothesis, what we're doing is we're also rejecting our claim. So we're going to say there is sufficient evidence to warrant rejection of the claim. There is sufficient evidence to warrant rejection of the claim that the average mean number of infections per week at a hospital is 16.3. Okay, we do have one more here that you can practice with if you would like. This one starts with a data set. So enter your data set in your calculator and get your summary statistics from your one variable stat. So you'll get these two values here. Our claim, we're using a 0.05 level of significance to test the claim that cell phones have a mean radiation level that's less than 1 watt per kilogram. So here's my claim statement in red. It's a claim about the mean, and we don't know what the population standard deviation is. So sigma is going to be unknown, and that means we're going to have to use a t-test statistic. And also a t-CDF to do the problem. Okay, so for checking our requirements, we are going to assume that it's normally a simple, we're going to assume it's a simple random sample. We don't know exactly that it is normally distributed, and our sample size is not big enough to get us around that. So if we look at the normal quantile plot, this is fairly close to a straight line, certainly not exact, but it is close enough for us to be able to go ahead with this. So if we set up our null and our alternative hypothesis, going back to our claim statement, we can see that the claim is that cell phones have a mean, so we're going to use mu, radiation level that is less than 1. So that's how we're going to set this up. We're going to have mu is less than 1. We'll use our t-test statistic, and we'll plug in the values for, this is the one we got from the one variable stats. This is from our claim. This is again from the one variable stats, and then this is our sample size. Be careful that you do use several decimals when you take it from the calculator. I would say a minimum of 3, 4 would be even better. Okay, so the p-value method, with this one, if we wanted to do this one just strictly on the calculator, then we can see that our we would do a t-test and we would get 0.3191 as our p-value. So if you're not asked to show the work for the p-value method, it is okay to get that from your calculator, but you do need to make sure you're choosing the correct type test. Okay, so on this one, if we compare our p-value and our alpha, we can see that our p-value is actually larger than the alpha this time. So we're going to fail to reject the null hypothesis. And because we're failing to reject the null hypothesis, if you remember our null and our alternative on this one, we had mu was equal to 1 and we had mu was less than 1. And so this was our claim statement. But we fail to reject the null hypothesis, which means we have to hold on to this. We don't have enough evidence to convince us or to support this alternative here. So we would say there is not sufficient evidence to support the claim that cell phones have a mean radiation level that's less than 1 watt per kilogram. So on the calculator, you can choose to do either your one proportion z-test for proportions, a t-test when sigma is unknown, or a z-test when sigma is known. Okay, that concludes a hypothesis testing with about the mean. So next class, we're going to look at hypothesis testing for variance and standard deviation, and then that will conclude our work with hypothesis testing. Thank you, and I hope you all have a